Hello, and thank you again for joining Ladies in Tech. We're going to look at part 3 of what is PLC. Before you go, please subscribe to my channel. Thanks guys, don't forget, subscribe. So the processor, the execution of the microprocessor function is referred to as a processor scan. So it's important that we know how the processor scans to understand how it's going to read our logic when we go to program it later. So on startup, the processor runs an internal self-diagnostic first scan. If any part of the processor system is not functioning, such as a faulty memory, comms, a fault light will come on. So you'll actually see on the front of the processor, and most of them, they'll have a fault light that comes on and says, hey, we got a fault. Once the processor has passed the self-diagnostics, the PLC begins to process scan shown below. So the first thing that the scan's going to do is determine the status of the input devices. So it's going to scan all those inputs and figure out if they're high or low and store those into the registries. Okay. 2, it's going to look at, it's going to interpret logic of the program and read and solve the ladder logic. So it's going to go through your logic. Okay. 3, it's going to update, turn on or off all the output to devices. So depending on what it interprets from your logic, it's now going to turn on or off the output devices. And 4, communication and housekeeping. So it's going to do all the communication and update all the registries and all that good stuff. And that's how it scans. Some processors have a watchdog timer, which sets time limits for each scan. And if that one scan takes longer than that time limit set for, it will put it into a fault condition. User memory. Storage available to the user for storing ladder logic, data file, I/O configurations, etc. in the controller. So that's where you're going to be able to store that stuff. Also, your files consist of system status files, I/O image files, and other user credible data files, the bits, the timers, the counters, the controls, integrals, string, etc. Storage memory, storage statuses, accumulated values, etc. Volatile memory loses when the power is removed. So anything in volatile memory, when that processor shuts down, it's gone. Non-volatile memory retains stored information when the power is removed. So we got to remember those types of memories, because when we look at timers and counters, those memories will either be there or not be there, and it's good to know where they're stored and how they're stored. So memory organizations. The PLC controls the user program repeated and accurately at great speed, and is done so by storing binary bits. There's 2 states, either 1 or 0. Make it easy to process either on or off, no in between. The processor memory consists of thousands of locations that are referred to as words. Each word stores binary data or binary bits. Words can be 8 bits, 16 bits, or 32 bits depending on the PLC. 8 bits is a byte, so you know, and an individual bit is a byte, okay? Or is individual ones are a bit, sorry about that. Okay, for example, PLC memory size is 256 words. Then it can store up to 4,096 bits of information using 16-bit words. All right, so if those words are 16 bits each, so you got your 256 words times 16 bits per word, or you have 2,048 bits using 8-bit words. Okay, so when somebody's talking about how many words, you always say, okay, let's talk about memory, how many bits of memory and how many bits of words. It's very important that you know the size of the word. When determining PLC system memory size, knowing the number of bits per word is important. Stored information is located by each word having a number and having an address. Addressing schemes also identify hardware location, rack, module, and terminal number. So for the here's an example for one of the Allen Bradleys that I get to work with, and data files. So output files, the identifier for it is always an O. Input files, it's an I, status file an S, a bit file B, timer file T, counter C, control file R. You can see on and on and on. And for this particular one, it will give you a file description. So it's really important when you're looking at your PLCs to know where your data files, where to find them, where to find your inputs, your outputs, and your other files as well. So always pull the user manual on your particular PLC that you're working on to get that information. So an example of a MicroLogix addressing template is here. We always have our file type. So our file type, there's several different ones we can choose from. I for input, O for output, T for timer, C for counter, etc. And then we have a colon, always happens there. And then the element, so your slot number. So where is that actual physical card? When it's on board, that's going to be slot 0. So when we talk about our fixed PLCs, everything should be a slot 0. And then when you got your modular, you're going to start numbering each of those slots in the racks. And then you have your the actual physical location, so your bit delimiter and your bit terminal number. Okay, so where it's actually hardwired to on the PLC. So this little drawing shows you in relationship for the address and the output devices. So if we look at this as an input module, L1, here's a switch, and it's wired to 12. You can see it's 12 here. And the input terminal is I13/12. So that tells me it's an input located on slot 13 on pin 12. And here we are addressing it. So I:13/12. Oh, we're running out of power. Hold on one second here. Okay, so now let's go look at the output card. So the output card we have here, and our output O, right, at 12/6. So we have a light coming in here on pin 6. Okay, and here we are addressing it. So O:12/6 is our output device address. So our data files, based on the input image below, so I actually went in and opened up the software and took a picture of the data file for the inputs for this MicroLogix 1400. And we looked at this, and I can say that this is for I:0.0. So this is for the whole 16-bit word for word 0 here for this input file. And we got a high at bit 2 and bit 4. So I got a couple statements here. Let's see what best fits. A normally closed push button wire to terminal 4 is actuated. So if we look at terminal 4, it's high. If it's normally closed, it would be high, but when we actuate, it'd be low. So we'd be expecting to see a 0 here in that situation. B, a normally closed push button wired to terminal 2 is not actuated. So terminal 2, a normally closed push button is wired there, not activated. Oh, yeah, I could see that being true. C, a normally open push button wired to terminal 1 is actuated. Well, if it's normally open and I push it, we should be expecting to see a high, and we go to 1, it's a low. B, a normally open push button wired to terminal 3 is actuated. So normally open, and it's pushed at 3, we'd be expecting a high, and we got a low. So our answer is B. This is just showing you how we can actually see the data files on the PLC if we wanted to. And that's all I have for you now for PLCs. I know it's a lot at once, but I'll keep showing some more stuff here, and hopefully I'm answering some of your questions. All right, thanks. Any questions or comments, please post them below. Thank you.